In this video, we're going to extend the WKB approximation to the turning points of classical motion. First, we'll review the WKB method. Then we'll look at the turning point solution, the patching functions, and then finally the fully patched WKB solution. So first we'll review the WKB approximation for potential wells with potentials of arbitrary shape. The wave function inside the well where E is greater than V of x can be determined using the so-called WKB approximation. And when we do that, we get the following wave function inside the potential well. Psi of x is equal to some normalization constant over the square root of the momentum times e to the plus or minus I over h bar integral of the momentum with respect to dx. This is the classical region. In the same way, when you have a potential barrier where E is less than V of x, the wave function is given by something quite similar. V of x is equal to the normalization constant divided by the square root of the absolute value of P of x, because P of x is negative, e to the plus or minus 1 over h bar integral of absolute value of P of x dx. Now clearly inside the potential well, the system looks like traveling waves in two directions. Inside the tunnel barrier, it looks like exponential decay and rise. This latter is the so-called non-classical region. So these solutions hold for potentials with hard walls, where the momentum is relatively large, and you don't have to deal with the energy becoming close to V of x. When E is equal to V of x or close to V of x, and you don't have a hard wall, then it's much more difficult to solve this kind of problem. So suppose that we have a boundary that separates the classical and non-classical regions, and it's not vertical. At this point, the WKB approximation formally breaks down, because the WKB approximation is saying that the potential is always far away from the energy. The difference between the two is large, and therefore the absolute value of the momentum, whether it be negative or positive, is large. So this is the case we're interested in now. We have an energy E, and we have a wall or a barrier, potential barrier, and the two are equal at the turning point. Over here you have the non-classical region where the energy is below the potential. Over here you have the classical region, and in here the WKB approximation breaks down. So we're going to treat this by first moving the x-axis to put the right-hand boundary, that is the boundary where the potential is rising, at x equals 0. And in that case, we can write now the WKB solutions for the classical and the non-classical regions in the following way. So we have, in the classical region, we have an incident wave and a reflected wave, and those are written here, 1 over the square root of the momentum times b e to the I over h bar integral from x 0 to x p of x prime dx prime plus c e to the minus I over h bar integral from 0 to x p of x prime d of x prime, where x is now negative, less than 0, so it's over here. So we're integrating out from the origin where the potential energy and the total energy are equal, down to a point x out here. That's the WKB formalism. In the non-classical region, we only have the decaying exponential, because you can't have a rising exponential in that region, and that is given by, the wave function is given by 1 over the square root of absolute value of P of x, d times e to the minus 1 over h bar, integral from 0 to x, absolute value of P of x prime dx prime. And this is for x equals 0, and so it's greater than 0. And so you start at this point and you integrate the potential out and you get your wave function. Now, if E is less than V for all x greater than 0, that is, this doesn't turn down, then we can assume that there's no transmitted wave through the barrier. And we're going to assume that at this point. So what are you going to do? You're going to match the classical and non-classical solutions. But the problem is where the momentum is 0, the WKB approximation breaks down. That is, psi goes to infinity. So what we're going to do in that case is we're going to carve out a region that's centered around the turning point where the momentum is 0 and use a different function called a patching function to patch together the WKB solution over here and the WKB solution over here with a continuous function that goes through the turning point. And that's called a patching function. And we're going to assume that in the patching region, the potential is linear. So the potential has a linear dependence on x in the patching region. So we can then approximate the potential in the patching region by E, which is the energy at the turning point, plus the derivative of V with respect to x evaluated at 0 times x. So that gives you a rising potential that's linear in the patching region. So if we choose the patching region the right size, this linear approximation will be quite good. And because we're using a linear approximation, we'll be able to solve the differential equation, the Schrödinger equation, and get a function. So that means if we're linearizing the potential, we need to solve the approximate Schrödinger equation that looks like this. Minus h bar squared over 2m d squared psi patching by dx squared plus the potential, which is E plus V prime at 0 x, that's the derivative of the potential at x, times psi p is equal to E times psi p. We can now cancel the two E terms because they're identical. And we get a differential equation that looks like h bar squared over 2m d squared psi p dx squared is equal to the derivative of the potential at the origin, or at the turning point, times x psi p. If we gather the constants, pull all these constants over together, we get d squared psi p by dx squared is equal to alpha cubed x times psi p, where alpha is equal to 2m over h bar squared times the derivative of the potential at the origin to the 1/3 power. Well, this differential equation has a well-known solution. And we can see that by making a change of variables from alpha times x to z, which means that dz is alpha dx, and this gives you the so-called area equation. That is, d squared psi p dz by dz squared is equal to z times psi p. So we basically eliminated the alpha in this way. The solutions to this equation are two independent area functions, ai of z and bi of z. And we'll take a look at those now. So ai of z looks like this. It's an integral equation. It's 1 over pi, integral from 0 to infinity of cosine s cubed over 3 plus s times z integrated by over ds. So we integrate ds over to infinity, and we get a function of z out. And this is what it looks like. So remember, this is the function in the classical region. It looks like an oscillatory function. In the non-classical region, the turning point being at 0, it drops off exponentially. bi of z is similar. It's 1 over pi, integral from 0 to infinity of e to the minus s cubed over 3 plus s sub z, s times z, plus sine of s cubed over 3 plus sc, all integrated over ds. And this looks a little bit different. This is still oscillatory in the classical region, but it grows exponentially in the non-classical region. So this is very similar to all the other functions we've seen before, where there's one function that drops down well-behaved to infinity, and the other function rises and blows up at infinity. So what we're interested in is not so much what happens close by the turning point or the origin, but we want to patch these functions to the WKB solutions far away from the origin, or far away from the turning point. So we're interested in what happens asymptotically as you move away from the turning point for each of these two functions. So when z is much, much bigger than 0, then ai of z goes like the following. 1 over 2 square root of pi z to the 1/4 times e to the minus 2/3 z cubed z to the 3/2. And bi of z goes like 1 over pi z to the 1/4 e to the 2/3 z cubed z to the 3/2. So we have one exponentially decaying function when z is much, much greater than 0, and one exponentially rising function when z is much, much bigger than 0. And that's what these graphs show as well. What about when z is much, much less than 0? Well, when z is much, much less than 0, then ai of z becomes 1 over square root of pi minus z to the 1/4 times sine of 2/3 minus z to the 3/2 plus pi over 4. And that's over here. It's an oscillatory function, clearly an oscillatory function. And b sub I is also going to be an oscillatory function, and as you might expect, it looks exactly like the function, except it's a cosine instead of a sine. So you have 1 over square root of pi minus z to the 1/4, cosine of 2/3 minus z to the 3/2 plus pi over 4. And that makes sense too. They're out of phase by 90 degrees. So the patching wave function, therefore, is a linear combination of the area functions. So we can, in the most general form, write psi patching, psi p, is equal to a times the area function ai of alpha x plus b times bi of alpha x. And in order to be able to solve the entire potential, what we have to do is match this function up with the WKB solutions that come from very large values of negative x and very large values of positive x. So the WKB approximation is good until you get close to the turning point, where on either side, and the patching function in between is used to match up the function over here in this purple region, this overlap region, and this function here in the overlap region 2. So the two overlap regions are where we've got to match psi p and psi WKB. So in these regions, all these regions, we're assuming the potential is assumed to be linear, but where the WKB approximation still holds. So in this region, this whole patching region is divided into 3 parts. The patching region is where the area functions hold. And then you have these overlap regions where you still have linear behavior of the potential, but the WKB approximation holds in this overlap region. So we're going to treat the overlap regions individually. Well, in the region where the potential is linear, we can now write the momentum for the WKB approximation. That is, the momentum is equal to square root of 2m e minus e minus v prime at 0 times x, because this is the potential. And when we cancel the two e's, we get the square root of minus 2m v prime of 0 at 0 times x. And when we just extract the minus x by itself in the square root, and we pull everything else out, we get, we see again this alpha parameter. And so we get h bar times alpha to the 3/2 when we pull it out of the square root, because this is related to alpha cubed. and then times the square root of minus x. So this is the momentum inside the patching region or in the overlap regions. Now, if x is less than 0, then clearly the momentum is positive. If x is greater than 0, then the momentum is imaginary. So let's first look at overlap region 2, where x is greater than 0. So we're going to compute the WKB function out to x, which is greater than 0, in overlap region 2. So we want to figure out what the WKB approximation is out here. And in order to do that, we have to integrate from 0 to x of the momentum of x prime dx prime, absolute value of the momentum dx prime. But we know what that absolute value of the momentum is. It's h bar times alpha to the 3/2, integral from 0 to x of square root of x prime dx prime. Because we've taken the absolute value of the momentum. And that means that we have, when we integrate this out, it's very straightforward. It's 2/3 h bar times alpha x to the 3/2. That means the WKB wave function can be written as follows. Some constant d over square root of h bar alpha to the 3/4 x to the 1/4 e to the minus 2/3 alpha x to the 3/2. Now, if you recall, because x is greater than 0, z is much greater than 0 in this case, the patching function becomes the following. Its psi p is approximately equal, it has the two terms, one is a decaying exponential, one is a rising exponential. And we have two constants here, a and b. And we have lowercase constants for the patching functions, uppercase constant for the WKB constants. So there's one slight difference. This has a factor of 2 and the square root of pi, alpha x to the 1/4 divided into a times e to the minus 2/3 alpha x to the 3/2 plus b over square root of pi alpha x to the 1/4 e to the 2/3 alpha x to the 3/2. Now clearly this term will not match the WKB function. And so we can right now, by comparing the two, see that a, which has this term here and everything else, the exponential looks exactly the same, we can equate the two constants in front, and we find that a, lowercase a, is equal to the square root of 4 pi over alpha h bar times capital D. And we also see that b is equal to 0. So that's overlap region 2. Now for overlap region 1, x is less than or equal to 0. So the WKB exponent is now, we're integrating out from x to 0, right? So we're just going to integrate out from the negative value of x positively towards 0, and that'll give us our value of x, of p of x prime dx prime. And for the same reason that we had before, because we can write down what the momentum is, it's related to the square root of x, we get 2/3 h bar times minus alpha x to the 3/2. And again, x is negative. And the wave function then, WKB wave function, has two terms. We have 1 over square root of h bar alpha to the 3/4 times minus x to the 1/4, all times capital B times e to the I 2/3 minus alpha x to the 3/2 plus c e to the minus I 2/3 times minus alpha x to the 3/2. So these two are the incoming and outgoing waves to the turning point. If we recall that b equals 0 from the overlap integral 2, and using the asymptotic forms of the area functions for large negative values of z gives us a patching function. And the patching function now only has one term because the cosine term, which is related to b, goes away. the coefficient is b, and that cosine term goes away. And so now we have psi patching is equal to a over square root of pi times alpha minus alpha x to the 1/4 sine of 2/3 minus alpha x to the 3/2 plus pi over 4. But clearly we can break this sign up into two complex exponentials. And when we do that, we get alpha over square root of pi times minus alpha x to the 1/4 times 1 over 2i. And then we have e to the I times I pi over 4 times e to the I 2/3 minus alpha x to the 3/2 minus e to the minus I pi over 4 times e to the minus I 2/3 minus alpha x to the 3/2. And now we can compare the WKB function and the patching function, and we see that the two exponentials are of the same form, and so we can equate the constants. And out of this, we get that a divided by 2i times the square root of pi times e to the I pi over 4 is equal to capital B over square root of h alpha. And similarly, we get that minus a over 2i times the square root of pi e to the minus I pi over 4 is equal to c over the square root of h alpha. Right, so we pick up the c and the b. Now, if you recall the solution for the upward sloping wall that we wrote down initially, we had, for x is less than 0, this is a WKB solution, we have 1 over the square root of p of x, b e to the I h bar, integral from 0 to x, p of x prime dx prime, plus c e to the minus I over h bar, integral from 0 to x, p of x prime dx prime, and then that's for x is less than 0. For x is greater than 0, we have 1 over the square root of absolute value of p of x, d e to the minus 1 over h bar, integral from 0 to x of absolute value of p of x prime dx prime. And using the results of the patching function that we just got to connect the coefficients across the turning point, remember, we now have results that tell us what d is related to lowercase a for the patching function, what b is related to a for the lowercase a for the patching function, and what c is related to a for the patching function. And we get the following. We get a is equal to square root of 4 pi over alpha h bar times capital D. Then we have a over 2i times the square root of pi e to the I pi over 4 is equal to b over square root of h bar alpha. And similarly for c, we have minus a over 2i square root of pi e to the minus I 4 pi over 4 equals c over square root of h bar alpha. And we can take these three equations and eliminate a. When we do that, we get that b is equal to minus I e to the I pi over 4 times d, and c is equal to I e to the minus I pi over 4 times d. So we've eliminated a, and now we no longer need the patching function. The patching function was only used to match the functions on either side of the turning point. So we don't need to know the details of the WKB function, because we can't, because the approximation is so good, but we use this patching function to match the WKB functions on either side. And so once the patching functions are no longer needed, the origin can now be shifted back to x2, that is to the other side, to wherever it is in the well, to yield the full WKB solution for turning point 2. Remember, turning point 2 is in the positive side for a classical well. And so we now push these over where the turning point is x2. Before we had moved it to 0, now we move it back to x2. And we get that the wave function for x is less than x2, that is inside the well, is 2d over the square root of px. And then we can combine these two together to get back a sinusoid. So we get sine of 1 over h bar integral from x to x2. So So we're integrating from where we want the function to the turning point. P of x prime, d of x prime, plus pi over 4. And that's on the left side of the turning point. On the right side of the turning point, we have d over square root of absolute value of p of x times the exponential of minus 1 over h bar, integral from x2 to x. So we're integrating out from the turning point, absolute value of p of x prime dx prime.